Hello, we're back. Unit 7, Section 4. We're going to complete pages 3 and 4. So we have the graph of the quadratic function right here. This is what they gave us, the x squared minus 5, and it's graphed for us right here. We need to find its inverse. Well, we have to determine domain and range and then find the inverse. And then we're going to talk about domain restriction when applicable. So for us to find the inverse of this quadratic function, we have to first switch x and y, which we did, and then we're going to solve for y. Add 5 to both sides, and then when you take the square root of both sides, it's always going to be plus or minus, and that's what I have here. So if the domain is all real numbers and the range goes from -5 up to positive infinity on both sides. What I have here, this blue line is the y equals x line, because I know that's important when we're talking about inverses, and we know when they're inverses when they're reflection across the y equals x line. And something pretty neat is they will also intersect at that y equals x line, and that's just easy to see. Okay, so the domain restriction comes like this. If we're going to restrict the domain, that means I'm only going to select here this portion of the quadratic function. So when x is greater than or equal to 0, I have only this part right here. So if I'm going to reflect only this part of the graph, I'm only reflecting this top part right here. It's like when I'm taking the plus or minus, then I'm only choosing, I wish I could erase this part. But if I'm only reflecting this, the reflection of this would be right there. Okay, but since I'm just restricting the domain in the beginning, then when you take the plus or minus, it would make its inverse not a function. But if you restrict, then the inverse of only this part of the function is only the positive side of the square root. Okay, the negative would be the reflection over the x, and that would be this part right there. That's why I only wrote as the answer for the inverse this part right here, because of my restriction on the domain right there. It gets easier as we progress. This is just funky, and I wish this wasn't the first one, but that's what we have. So off we go. So now this one is the function of a square root. So the parent function would have been just square root of x, which that's nice. But then we have this function right here. We need to find its inverse. The domain starts right there at 1.5 and goes up to positive infinity. And then the range is from 0 up to positive infinity. That's what we have here. And remember, from the previous video, we talked about how the domain and range, they switch. So when I talk about the range from the original function, that's going to be the domain restriction of its inverse. And we will talk about it when we get there a little bit more. So let's algebraically find the inverse of the square root of 2x minus 3. First, we're going to switch x and y, and that's what we did there. We're going to raise both sides to the power of 2, like we've been solving from section 3. You will add 3 to both sides. You will divide by 2, and that's where we are. Okay, I just rewrote this in decimal, but this is the same as this, which is nice. So if I were to graph this function, it would look like a quadratic function right here at 1.5. It would be right there. And you can clearly see that if the y equals x line would be right there, this is the reflection over this within reason, because I have this extra part of the quadratic function right here that just doesn't exist from the original function. That's why the domain restriction is necessary here. That's why the range from the original function is now the domain restriction of your inverse. So even though this is part of your quadratic function, it should be a little bit slider right there. So I'm only considering this part of the inverse, okay? Just where x is greater than or equal to 0. And that's a true inverse function right there. Watch out for the domain restriction. The next one, I have the square root of 4 minus 2x. We're going to have to switch x and y, which we did here. Take away 1 from both sides. Raise both sides to the power of 2. And then in the same step, I just swap the order here because the goal is to solve for y. And then, you know, x was on the left side. It was yeah. So I have to minus 4, and I did. And then you have to finally divide by negative 2 to isolate y. So you have an invisible 1 here. Divide that by negative 1 by negative 2. You don't even have to expand this because that's just too much work. And it's easier to graph our inverse like this. And you don't even have to graph the inverse. It doesn't say that we have to. But just be careful because here we have the domain of the original function, which is from negative infinity approaching 2 up to 2. And then the range is from 1 up to positive infinity. And that's going to be your domain restriction right there. Because when you graph this function, is going to be like this, 1 to the right and up 2. It's going to be something like this. So then I'm only getting, oh, I erased the wrong part. 1 to the right, upside down, up 2. So I'm only getting the part that is greater than 1. And then the y equals x line will be right there. So they kind of would go right this. I wish we had a better graph, but we don't. So we just deal with it. So if the whole quadratic function was like this, I'm only choosing the part that is greater than 1. So only this part would be the inverse when I'm looking at the original being a square root function. Okay? I think it makes more sense now than it did with the first one. Now, it's nice when I have a cubic function here because there's no domain restriction because the domain is all real numbers for both, so that's nice. This is my function. Again, I switch x and y, I add 3 to both sides, and then I cube root both sides to get rid of that cube right there. And there's no plus or minus, so it's just beautiful. Easy, no restriction. Booyah. Let's keep trucking. So right now we don't have the graph for us to look, but we can always just sketch the graph real quick. Or just look at the range from the original function. So let's solve, but this one we don't have to worry about it because it's a cube root, and cube root, both my domain and range are both all real numbers, so no domain restrictions, so that's nice. Switch x and y, raise both sides to the power of 3, add 1 to both sides, and done. It's nice when I don't have to worry about the domain restriction. But it's not the end of the world either. So here I have this one. I'm going to restrict the domain here because if I were to graph this, this is my x and y. My original function would just be there, somewhere over there. So when I solve this, I'm taking the square root of plus or minus. Your reflection would be like this. That's the inverse, okay? But if I'm restricting the domain from the beginning, I'm only using this part of the quadratic function. That means when I'm coming up with the answer, I'm only going to use this part of the radical. So you can leave it like this, but you know, when you graph, it just looks a little weird. And we're not really that picky about the plus or minus here in the restriction of the domain when you start off with a quadratic function. But the process will be the same. You're going to switch x and y. You're going to minus 5 on both sides, divide that by 2. This looks like it's a good question to put in the homework. Divide that by 2, and then square root. So, but just be careful with the domain restriction there. Here, easy domain restriction because you start off with the square root, and then the range from your original function will be your domain restriction from your answer. So switch x and y, square both sides, minus 6, and that's it. It's going to be a quadratic function with the restriction as long as x is greater than or equals 0, just like the range from the original function. Last one. So here I have the domain, because in reality, what makes the domain? How do I find the domain here? Let's start there. So when I set this equal to 0, then I solve. Multiply by 3, I got 0, and then plus 7 divided by 4. This is where my radical, this is where the start, that's the starting of the x right there. So when you graph this, it would be somewhere over there where 7 over 4 is the beginning right there. Oh, it goes the other way. Because that negative right there. So, and then the range is everything from negative infinity up to 0. Okay, there's nothing wrong with you sketching the graph and see what it looks like. It's just easier to have the visual there. So that's where I got this 7 over 4 from. It's when you make this 0, you know that's going to be where your graph is. So switch x and y. You divide by negative 3. You raise both sides to the power of 2. At this point, when I was raising this side, you have to raise everything on that side. So not only the negative, but the x and also the 3. When you raise a negative, that makes positive, and then 3 squared is 9. And then when you raise this side over here, they're going to get rid of the square root, so that's nice. Cross multiply, so I got 3x squared right there, and then I multiply 9 times 4y, I got 36y. 9 times 7, I got negative 63. Then we're solving for y, so plus 63 there. Divide everybody by 36. Remember to simplify the fraction. And here we are with the 7 over 4, right there from its inverse. So the inverse will be somewhere over here, considering the domain restriction, where I'm only using x is less than or equals 0. So I'm only using this part of the graph right here. And here will be my y equals x line right there. So boom, that's your reflection right there.